Maybe we should get going already. So great to be here today, and yeah, glad to be here. Uh, and welcome to this webinar that we are hosting here at the ICR with Crop Intellect on the methodology that is in public consultation at this moment. We will run this webinar for approximately an hour. We'll be in two sessions, an introduction about the ICR methodology approval process. Then we'll hand it over to Crop Intellect, and they will do a presentation of the methodology that is under public consultation and under approval process, introducing the atmospheric nitrous oxide destruction using photocatalysts that is developed by Crop Intellect and is following the methodology approval process. Then we will conclude with a Q&A session that would range for approximately 20 hours.
20 hours.
20, yeah, 20 minutes. Thanks for that. So the session is recorded, and the recording will be made available after, hopefully before the end of the week, and available on the public consultation page. You can, during the session, just at any time, raise your questions through the Q&A button at the bottom of your screen. There's a Q&A button that you just click and submit your questions. So, yes. All right. So today we'll be exploring the novel methodology for quantifying the destruction of atmospheric nitrous oxide using photocatalytic technologies on crop surfaces, a groundbreaking development in agricultural climate mitigation. The ones that will be doing the presentations is me, I'm Guðmundur from the ICR, then from Crop Intellect, Apostolos Papadopoulos, sorry for destroying your name, and Alvaro Montero Bocos. Apostolos is the founder and director of Crop Intellect, and Alvaro is the CEO of Crop Intellect. I will then now go ahead and now go through ICR presentation. So what is ICR? ICR is the International Carbon Registry. We are a greenhouse gas program. We have methodology projects globally. There are about publicly on a registry about 120 projects, both local here in Iceland and international projects. There are about 48 under development and 40 plus 44 that are under validation, and 30 validated. We, as you may know, we rely heavily on ISO standards in our program, and for a project to be registered with the ICR, project need to adhere to ISO 14064-2 and the ICR requirement, and for that they can apply a methodology. The methodology approach is then we have approved methodologies that we refer to as, for example, CDM methodologies, active CDM methodologies, then ICR methodologies, all the methodologies that can be used as a good practice guidance or establishment of criteria and procedures within the project documentation. But a little bit about that, this approach, the ISO 40064-2 is like brings like the foundation of a good quality carbon project. It sets out requirements such as for the description of a project, establishing the baseline scenario, boundary, determining the sources, sinks, and reservoirs of the project, how it's quantified, monitored, management of data quality, and then, of course, the reporting requirements. It's not a carbon market standard, it's a carbon process standard. So that in the ICR requirement document, we address the limitations of that ISO standard, and such as eligibility of project registration, safeguards and SDGs, how we approach additionality, permanence, double counting, grading, and more. So about the methodology approval process. So our vision is to be inclusive, not exclusive, for project and methodology development. We promote that if solutions have the potential of being impactful, we really welcome all methodologies into our registry. So supporting innovation in the climate space. Subject to, of course, that they adhere to our requirements. So what is a methodology? So as I described before, on the as a core criteria for the registration is the ISO and the ICR requirements. So methodology, I often describe methodologies as a recipe, recipes for baking a cake. So methodologies are recipes on how to create a consistent climate or carbon process. So it outlines criteria and procedures on how to measure and calculate emissions reduction removals. It defines approach to determine the baselines, monitor emissions, reporting, and ensuring that they are verifiable. Methodologies, they include, and they all do, a scope of application, their applicability conditions, some normative references, definitions that are in addition to definitions that you would find within the program and the ISO standards. Then the baseline and the project scenarios, identifications of sources, sinks, and reservoirs, how to address additionality of projects that apply the methodology, boundary quantification, and monitoring. So relevant documentation relevant to the methodology approval process. So of course, for the project the project documentation is, of course, in addition to these documents. So on the requirements, that those are ICR methodology requirements, the ISO 14064-2, and then terms and conditions that apply for working with us. Then there is this methodology approval process that I will go into in a bit, and to support this is our ICR definitions. And for consistency's sake and efficiency, we have, of course, templates like everybody else, and comprising of methodology description and concept note, and also we have something called the methodology summary document. So the process of developing a methodology is that, and the Crop Intellect, we have had the privilege to working with Crop Intellect for some time now, starting with a submission, which is optional, submission of a concept note. We then give a feedback on that concept, like guiding on any rabbit holes or any guidelines on the language, maybe some consideration that the developer should focus on. Then it continues into the actual development of the methodology. The methodology needs to be validated by a third-party VVP, and we are working with numerous VVPs that have the competence in validating a methodology. Then it's the public consultation, which we are currently doing with Crop Intellect. We we sometimes allow, or like we it's an option if a methodology chooses to start the public consultation prior to the validation or post the validation. Then it's the our final review of the methodology documentation that comprises of the methodology and the validation report of the methodology, focusing on the language and the consistency of the methodology, and then the final or board approval. It also comprises of an application of the methodology at the project level. So, so the developer knows if there are any challenges in its application at the like practical application of the methodology. So we would rather have that that the developer would address any inefficiencies in the methodology prior to finalizing the methodology, because sometimes it may lead to that inefficiency in its application results in that revision of a methodology, and that it's a more costly process. So application of the methodology, validation of a project, we will do then from the project level a review similar to just the same process as we do with project registrations. So it comprises of, as I said, with the documentation, the methodology requirements. They like highlight just the requirements from the ISO 14062 and the ICR requirements at the methodology level rather than the project level, like what needs to be included, like references to other methodologies, summary description of the methodologies, definitions, applicability conditions, boundary, baseline scenario, additionality, how it's how it's quantified, monitoring, and then the requirements relating to the implementation of the process of the project. And then on the left side is the methodology approval process, but which I just described in the previous slide. And for the methodology description template, that is for, as I said before, consistency, and that like aligns, like the methodology description template aligns then with the methodology requirement document, that you would see that where you put the applicability conditions, the boundary, etc. So then the criteria for the validation of a methodology are ISO 14064-2 at the methodology level rather than at the project level. So that means that the assessment is that what's the opinion of the VVP that application of this methodology leads to conformity to the ISO 14064-2 at the project level, and then the ICR methodology requirements. So for further information about the methodology approval process is found on our documentation page under methodology development. So for transitioning to the crop Intellect team, we would see that now the methodology is under public consultation, and we encourage all stakeholders to give feedback so crop Intellect can take into account any considerations or any improvement that stakeholders may have to improve the methodology. So you would find the public consultation page under the ICR program at the top here on the screen. Then it would take you to the documentation page, and you would find and it's behind the screen, not good design. You would find that under methodology development, under public consultation, and it should appear really early if you go into public consultation. and we'll share, of course, links afterwards. So that concludes my presentation about the process that methodologies go through with the ICR program. But now I want to hand it over to Dr. Apostolos and Alvaro that will take you through the presentation of the atmospheric nitrous oxide destruction using photocatalyst methodology. Thank you. No, please unmute yourself and go ahead with the presentation.
Yeah, thank you very much. Just loading the presentation. There we go, that should be visible. Hello, everyone. Thank you for the introduction to the ICR and how it works and our collaboration. We have developed the methodology, which is a photocatalyst that removes N2O. That's a distraction. The company is called Intellect, and I'll introduce the company a little bit so you understand the background and the branding, if you like, of the specific photocatalyst that we're talking about is RLIF. So Intellect was formed in 2011. We developed technologies that improve crop sustainability, increase the output and reduce the inputs. And the core is to patent these technologies so that we can work with multinationals, with companies that can have a global adoption and also increase that impact that we can have. The company's mission is to make a positive impact to the world's agricultural sustainability for a secure future using innovations that are out of the ordinary. And RLIF is such an innovation, is our third patent portfolio, and is based on photocatalysis that is used in agriculture and is something that hasn't been done before. Just a quick introduction. We are a small team but comprised of researchers, scientists, and project managers. You will meet Alvaro in the following slides. So the photocatalyst breaks down NOx and N2O. Photocatalysis in general is where a light with usually high intensity, so UV light hits a mineral, and then we have some surface area surface charge created, and these are classed as electrons and holes or superoxide anions and hydroxyl radicals. These have the ability then to react with nitrous oxides, and typically they break them down. So we have the, importantly, N2O breakdown into N2 and O2, which are inert after we destroy them, and NOx pollutants, which always talking about the background, the atmospheric background levels can be converted to nitrate. And that's very relevant for farming because then we can reduce the amount of nitrogen that is used. And that is typically about 25%, which equates to 50 kilograms per hectare. So that's the reason the farmers are interested already in putting this new material, if you like, in agriculture on their crop. So a little bit more in detail as to the N2O breakdown. You know, we are one of the very first methodologies that focus on N2O. Typically, others are looking at carbon dioxide, a few in methane. And the way that the N2O is equivalent to carbon dioxide is multiplied by 300. So the global warming potential is 300 times that of carbon dioxide. The breakdown, once we go through the methodology as to how we measure, we have evaluated that and calculated and measured it to be between 2 to 5 tons per hectare of equivalent carbon dioxide. And that's the potential of the destruction that we provide and the impact. You will see on the picture what the photocatalyst looks once it is applied on the foliage. That's on the right bottom where you see the leaf. And just to talk a little bit more about the technology, the photocatalyst is based on titanium dioxide. That's one of the most potent photocatalysts that's been studied. And we have a special process so that it works under visible light, which means outdoor light. So the N2O and O2 that is then as a byproduct is not to be reformed, if you like. So that's a permanent removal. And that's in a volatile form. The photocatalyst has been prepared in a formulation that is liquid and is easily added into the spraying tank. So farmers can just use it with the normal equipment that they have and add it in the spraying tank, which is the inputs that they use in with other inputs, being fungicides, insecticides, or other fertilizers. And once that is sprayed, then it sticks on the foliage and remains there for up to 6 weeks. And there are typically 2 or more sprays. We're putting 1 liter per hectare. This delivers over the period of the crop life about 1 kilogram of the titanium dioxide. More can be applied as it is in the provisions of the methodology, but that's more on the detail. Now, if we ask why this methodology, why did we develop this as part of the solution? 30% of the world's greenhouse gases are coming from food and agriculture, of which 74% is anthropogenic, N2O, again relating to agriculture, and then 43% of the agricultural emissions are actually linked to synthetic nitrogen fertilizer use. So farming is quite a big part in the responsibility of the emissions in N2O. And this methodology allows the farmers to actually reduce that. And these the methodologies that are out there and typical practices in agriculture, they reduce emissions or avoid emissions, but it's not a distraction like we are. So we are removing directly N2O from the atmosphere, and that is measurable, permanent, and at scale. So I would like now to introduce Alvaro, who is going to talk a little bit more about the actual methodology. Thank you.
Hi, everyone. Oh, someone needs to mute that. Yeah. Thanks, everyone. Thank you very much, ICR, for the introduction. Thank you, Tolis. So we're very happy to be here today to introduce the methodology for ICR. This is the ICR number 11. So this methodology, we have been working for the last 2 years in developing this methodology. We have been working with Imperial College, with Cambridge Environmental Research Consultant, with Ostrava University, so with a number of stakeholders and partners very interested in understanding how N2O can be removed at scale. And one of the key elements and most challenging elements of measuring N2O, which is a very complex process where we are really at the forefront of that field. And we're very happy for stakeholders also to support us in the effort of how to scale measuring N2O at the scale in the future using a very innovative way of destroying N2O as we're doing with our leaf, with any photocatalytic material. Let's go a quick overview on the methodology. As per the work we have done with ICR, the category, the type of methodology is reduction, avoidance, and destruction methodology. Is primarily we're using for agriculture. And what we're trying to enable here is the quantification of the N2O that is destroyed during a project using photocatalytic materials, not only leaf, any photocatalytic material that has that characteristic of being able to break down N2O, which is not all photocatalytic materials. So in our case, as mentioned before by Tolis, need to be doped in a way. It's a patented technology, meaning that that we want all photocatalytic technologies to be able to develop projects, but need to have some characteristics that demonstrate that actually they can remove N2O. As mentioned before, technology agnostic and applicable globally, meaning that in terms of boundaries, geographically, we don't have any limitation. Mostly, we really need to be used as a methodology in agricultural activities, grassland, and similar surfaces, so we can have that impact. The main aim of the methodology, again, we are the first one trying to do something like this, is to enable this verifiable N2O greenhouse gas destruction in agricultural fields, and mostly on the elements of quantifying how we quantify that destruction of the ambient nitrous oxide using photocatalytic materials. I'm gonna be walking to you through the methodology in terms of the monitoring, which is another element of interest of the methodology, how we are doing the quantification of the impact, and also some of the characteristics of how a project gonna look in the future, and how the methodology is able to bring a number of co-benefits, a very, very scientific approach of the quantification of the removal of the destruction of N2O, and I'm gonna walk to you a little bit more in detail in the next slide. So we always think that the best thing is to do it a little bit more practical. So let's talk about how a project could look like applying this methodology. So let's say we are based in the UK. Maybe we didn't mention that, but we are in Lincoln, UK, and we work with we're very proud to be able to work with very strong partners around us, very strong farming organization around us. So let me talk to you about one of our partners, non-naming partners, but we have around 1,000 hectares of barley growing near us. In this project, what it involves is we're going to be applying, in this case, our leaf, but a photocatalytic foliar spray on the crop as a normal practice. We, by design, want the material to be applied with other input. We don't want the farmer or the organization to have to do an extra activity, also because elements of increased carbon footprint, but also the practicality of the organization to actually being able to deploy a technology like ours. We want that to be a very easy application. So the farmer will be able to apply that application of our leaf with other inputs. Normally, we recommend 2 liters of our leaf in two applications. So 1 liter in, for example, T1 and 1 liter in T2. That's the standard procedure that we recommend to farmers. Then what we require, as mentioned, is an active cultivated agricultural land. That's what we work best, and that's what we have done all our research, because the scalability of working with agriculture is much higher than potentially other surface that we could have used. So agricultural land is where we are mostly focused. In the monitoring and validation, in this case, what the team, the project developer, will go to the field, and we're gonna be taking air samples. Okay, I'm gonna explain more in detail, but the idea is that we're gonna take a flux gradient, taking an air sample in the canopy at canopy level, and then 1 meter or above that measurement. So we take 2 samples, one at canopy level, and then 1 meter or above. Then those samples are going to be taken then for analysis and calculation. But let's not go that much in detail at this point. But the idea is a very easy to apply process in terms of the monitoring. So we're going to go there, and then we're going to be able, the project developer going to be able to measure on site what actually is happening there in the field on the N2O levels, compare treated and untreated fields, so we can see the effect of the photocatalytic material. Okay. Then after that, of course, will be a process of validation, and then ideally everything gonna be up to standard. We're gonna be following the process and procedures of ICR for product development and our own methodology, of course, and everyone we're gonna be able to validate the results. Now, some conditions that need to happen in order for a leaf to actually for the methodology to be applied. Of course, the material need to be applied. It need to be applied in agricultural fields. They need to be applied when the canopy, the crop, or the canopy of the crop is grown. Normally, we recommend around 80% leaf coverage already. So if we apply in at the stage where there's not a lot of leaf, there's not going to be a surface for the material to sit on and do the effect. Project, for example, is not applicable to very shaded areas or non-vegetative surfaces or short-lived crops. Normally, we recommend that this need to happen in crops that at least have like 4 weeks of leaf leaf cover. So that's why we normally apply mostly on cereals, potatoes, and other crops that have a longer period of time for growth, so early can have the full effect. Okay. Next one, Tolis, please. Let's go to the different elements of the methodology that could be of interest. In terms of the baseline, for example, here's an element that we trying to provide product developers with a couple of options. In this case, we have been working with different partners, and again, a couple of years working in the methodology. And on the baseline, the baseline essentially is nothing happened. The standard farming practice occur, and they put their synthetic fertilizer, and they don't do anything because to really destroy and do, not going to be any activity beside, in this case, our intervention. What we provide in the baseline is an element of, it can be taken in 2 ways. One way is we spray our leaf in a treated area, and then we have a control, meaning that we're going to be able to measure that flux gradient that I mentioned before of N2O in the both elements, in the treated and the control, and then we're going to be able to make a comparison. That is one way of establishing a baseline. The baseline will be the control, of course. Then on the other side, and this is something that mostly for big scale projects, and in the future we propose in our methodology that the baseline is based on the carbon footprint of the farm. So what have happened before the intervention as a whole. So we believe that for scalability of the methodology and the project, it could be a very good way, and feedback has been positive in these 2 approaches. Next one. So you can see here, this is a little bit when the intervention happens. So the N2O is emitted in the agricultural field, then the photocatalytic material, the intervention using photocatalysis occurs, and then there's a destruction of that N2O that has been happening in the agricultural field. And that's a little bit the very, very basics of the price. So as you can see, very, very easy to implement, very farm friendly, and very, trying really to understand how a farm organization will really be able to implement something like this in a very easy way. Now, let's go even more in depth, because the monitoring part, we believe, is an interesting way that we're trying to approach this. Again, as mentioned before, N2O, measuring N2O on the field is challenging, it's complex, and we're very lucky because working with Imperial College and Cambridge Environmental, those partners are really helping us to develop this methodology in a way that is, in line with all the standards and able to really have a very strong scientific evidence. So in this case, as you can see in the image, the first idea, we're going to go to the field. As mentioned before, product developer goes to the field, and then we're going to take 2 air samples, one at canopy level, as you can see in the picture, and then above, a meter or above, we're going to take another air sample. We're going to have elements that are going to have an impact, and then that's going to be more in the calculation side. We're going to use air pumps and then Tedlar bags, the technical bags to take the air samples. And we're going to take those measurements over time during the day. Normally, we take in one sample day, we will take around 8 to 10 bags. And you have to think that when you're going to take a sample, we recommend before 5 days, but there's a range there that is acceptable to take samples after application. So normally we will take three samples or more. But again, in the sampling, in the number of samples is something that it's a range that it be required also during the process. You can take those three, and then you're gonna, in each moment of those three, you're gonna take 10 air bags in that way, no? And you're gonna have a control, and you're gonna have a field treated with air leaf. Then with that, those air samples, you're gonna be able to then input them in a specialized equipment. In this case, we are using LICOR equipment, but there are others like GasMet and GCMS that are also accepted, because we're really looking for high sensitivity sort of equipment. We cannot have, right now we're measuring very small variances in the changes, so we really need high sensitive equipment. And LICOR, for example, in this case, have been working great for us. Then with those, the data what we obtain from the air samples in the LICOR or any other equipment, then we will be running that through the calculation that we have been working with Cambridge Environmental, and that's gonna give us the tons of CO2 equivalent. That's different, that destruction of N2O. What that means in tons of CO2 equivalent, following equations that are based in scientific evidence and peer review papers, and working with, again, Imperial College, Cambridge Environmental, in developing those equations to be able to translate that in a tangible for our partners in terms of tons of CO2 equivalent. Next one. Other elements of the methodology that are important, project developers are going to have to show additionality. In our case, of course, that level 1, 2, and 3 are already there. It's true that it will not occur, the destruction of N2O will not happen without the use of photocatalysis. There is not really, at level 2, there is not really a requirement right now to be using anything like gas. And again, in terms of technological barriers or common practices is something quite clear in this methodology. Now, something very interesting is about permanence. You are quite aware of other sequestration methodologies, maybe. That's why we have to call ourselves a destruction methodology, because in our case, the permanence is real, it's tangible, because the destruction of N2O, so we break down N2O into N2 and O2, it doesn't revert, it doesn't come back unless it's into very specific conditions that are not natural conditions. It needs to be some elements of pressure or, for example, temperature, but that doesn't happen naturally. So there is not a way back to N2O again. So the permanence is very clear. There's no way back to the N2O form naturally. So those elements are really differential from any other method you may have seen around. It's the first time that this sort of photocatalytic materials have been applied at a scale to remove N2O. And that's why that is a number of elements of uniqueness of this methodology. Next one. And then just a little bit more on the overview of other elements that we bring into the table. Mostly this could be of interest as well for potential project developers in the future. We have a number of co-benefits that are very interesting for the projects and for the partners working with us. For example, as mentioned by Tolly before, we are able to break down or convert NOx gases, so a pollutant, mostly NO2, into nitrate, which is a fertilizer, is something beneficial for the crop. So that is a very strong benefit. You're cleaning the air, you're providing fertilizer to the farmers. That easy implementation, that really for the input from the stakeholders is very valuable, because you're going to be able to demonstrate also with the methodology that you're cleaning the air, not just only of a greenhouse gas, which is great, but also of cleaning the air for health diseases, etc., like NOx being a pollutant. Mentioned before about the elements of, can you go back for a second? And then, other elements like co-benefits, such as the very easy integration of farming practices, and a number of supporting all the SDG and net zero objectives, with bringing both the cleaning the air elements, that low fertilization, thanks to our leaf or to the photocatalytic material that is applied. There should be a reduction of synthetic fertilizer as well, if possible. So that's another co-benefit that we can bring to the table. Final one. And just a very quick overview what we're trying to do this season. Once hopefully we have our methodology approved with ICR, which will be great news. Today we have been able to work already with partners in the UK and in this case Hungary, but we have other potential commitment in the future because people are very interested. They know that it's easy to apply. They see that the potential to scale an impact of removal of N2O is very big, and they're very happy with the product so far. So we have been able to develop around 2,000 hectares right now in the UK with partners locally. So we want to really see, we want to obtain more data, we want to understand more in depth. But so far, partners are really eager, very involved, and we're really happy with the outcome so far. So this is our season for 2025, and I think this is me. So thank you very much. I think I've been talking a lot. Thanks. And now questions, please.
Thank you very much for this informative presentation about this impactful, hopefully, methodology and will be adopted globally. So there are some questions that have been submitted through the Q&A, and I'll try to navigate them. That's here on my other screen. So sorry. So this one. This methodology is quite unique in directly destroying atmospheric N2O using photocatalysts. Could you elaborate on the main scientific challenge in measuring such destruction reliably at scale and how the methodology addresses it? Thank you. Somebody that wants to take this. Alvaro, I think you're muted.
No. Yeah, I was muted, but Carlos also is gonna reply to the question.
Yeah.
Go ahead, Carlos.
Yeah, happy to. I'm Carlos, I'm a senior scientist in Intellect. Yeah, there is a very good question. It's a very challenging actually because normally photocatalysis is something that is normally done in the lab because you need normally high intensity lamps and very constrained environment so you can control everything and you can evaluate how it works and so on. So it's really challenging. But it's also good. The good thing in our methodology, I think, is that the photocatalyst is sprayed very well on a very big surface. So that helps a lot in terms of not only the exposition of the catalyst to the light, which is very high. There's no the penetration of light that usually is a problem when you have beds of catalysts and so on is not a problem in the field. And also you have a constant in an agricultural field, you have a constant feeding of your molecule to destroy in this case. So you can consider you always have the molecule there, so it's not going down as in a normal photocatalytic reaction. And then the highest tension of the agricultural field also helps in quantifying because one of the problems is actually to detect the small variation of concentration, but in this case, it's small concentration the small conversion that we can get on the field because of the tension of the field can be really significant. So it's very important to get the performance of the catalyst at scale and to be able to evaluate the removal. So yes, so it's quite challenging.
Thank you. Second question now. How does the nitrogen benefit the farmers directly? Is it stored in the leaves, the atmosphere, etc.? Also, how does the atmospheric condition impact the sampling variability?
Yeah. I'll take this. Just have to.
Yep.
Okay, that's better. Yeah, so the photocatalyst breaks down nitrous oxides as NO and NO2, the NOx to nitrate. And that nitrate is basically formed within the photocatalyst. Then it requires some moisture, which sometimes is enough, just the atmospheric moisture to solubilize that nitrogen to become then available straight away on the foliage, because that's where the photocatalyst is. If it is in the event of a rain, for instance, this can go into the soil, which then is taken up by the roots, but it's a very efficient way of the crop being able to absorb that nitrogen. The way that the nitrogen is provided to the crop is very different to the typical one. So farmers usually would either spray nitrogen that is liquid or in prills at quite high amounts. That causes, a lot of effects to the soil health, to the crop as well, from a crop physiology point of view. The way that R-leaf or the photocatalyst provides the nitrogen is on a daily basis, small amount, and therefore we're changing actually the crop physiology to be able to resist more, if you like, bacterial or fungal attacks, from the point of view that if the farmer reduces the nitrogen that they apply as a standard, the crop will develop slower, so it doesn't have that burst of growth because of the availability of nitrogen, and therefore the plant cells don't stretch and you don't have that fast biomass development, which also can cause some of the mineral deficiencies, which then relate to other issues that result in the poorer yield. So that's the first part of the question. Carlos?
Thank you. So the second part was, how does the atmospheric condition impact the sampling variability?
Yep. Just to answer that, is of course it's very important, the atmospheric condition, because we're measuring the field directly. So for a starter, I would say we avoid raining. If it's raining, we don't measure it, also because it can affect with the instruments and so we try not to measure raining. But after that, there is one important thing on the atmospheric condition, which is the variability of the N2O concentration in air. But that's why we're sampling within 1-2 minutes, because you saw in the methodology. So we account for the short-term fluctuation that's normally will be happening in the atmosphere. So we account for that in every sample that we take, in every bag that we fill in that time. So we account for that variation, and then we also this 1-2 minutes is long enough to account for that, but short, so we can collect 8-10 samples in a short time, so the weather condition doesn't change that much. So we will do that everything in around 15-20 minutes. We avoid weather variation, but we still have enough time to account for short-term fluctuation, and that's how we account for that variability.
So here's one that is came a little bit into this in the presentation. How is N2O destruction different from reduction or storage?
Yeah, I can take that one. So, as mentioned before, during you may have seen a number of other methodologies or techniques to sequester CO2. In this case, that is sequester in the soil. It's a storage there. But while there's a long duration to that, it's true that eventually that could come back to the atmosphere. In our case, it's not like that. It's atmospheric gas, N2O. We destroy the molecules, and in order to revert that process, we have to be in natural conditions, like of very strong pressure or temperature. Things like that will not happen. Okay. Then there are other elements like avoidance methodologies out there. Again, the very, very, very positive thing of our methodology is that we are compatible. So it's not one or the other. So you don't have to do a photocatalytic project with us or with our methodology and then don't do a biochar project. You can do both at the same time, and you're going to have a very positive impact. You can, for example, with our material, as mentioned during the presentation, there's a chance of reducing the synthetic fertilizer input, which is gonna also have an impact using Vera 42, for example, that can help also to the carbon footprint, to the generation of credit if needed. So we are there for as an addition, as something that is compatible with all other elements that are applied in farming. So yeah, it's a permanent destruction and very compatible with any other methodology out there to reduce or avoid emissions in agriculture as well.
Okay, thank you for this answer. Yeah, another question here. Does air sampling needs to take place in every field included in the project?
Yeah. Yusuf, would you like to take that one?
Carlos.
Carlos, sorry. Yeah, confused.
Yeah, it's question. It's not necessary because there is a rule in IPCC of representativeness that is a surface is homogeneous enough, and agricultural fields are considered very homogeneous. You don't need to measure all the surface to account for the removal. You can normally measure, you just will need to measure 2 to 5% of the whole project area in order to represent the whole total area of the project. So that's as an example, you have 1,000 hectares, for instance, project. You just need to measure 20 to 50, which is basically one measuring point in our case, to account for the whole total area of the project in terms of surface.
Just a follow-up question here for me. Do you randomly distribute the sampling site or?
We try to put it on the center of the field because the footprint of our methodology is already around 10 hectares. So you take air from we measure around the center of the field, a bit downwind. So we account for the air coming from 100 to 100 meters upwind, and then we account for an area, a total area around 10 hectares minimum. So we just need one point around the center of the field to actually measure this.
Any US farmers in any pilot yet?
Yes, yes, we have had some. So as mentioned before, the product has been in development for the last 6 years. It's a product that has benefit, that is a good agricultural product for farmers. So they like the health that can bring to the crop. So now with all the elements of the agri-food supply chain being interested in reducing emissions at farm level, we have a number of local partners working with our product where we go there to take data to understand more about the end-to-end destruction that is happening. So yeah, we have right now a number of several pilots, both in the UK, also in Europe, that we were showing before to you and to everyone. So yeah, the interest is growing, and hopefully we're gonna be able to have the projects ongoing in the next few weeks.
Sure. So we are closing in on time. So there's one question from me here,
Yep.
and I wanted to close with. As this methodology moves through public consultation, what kind of feedback or input from stakeholders would be most valuable for you to refine the methodology further?
Yes, so mostly for us, there's an element, very important element from at farm level, for example, implementation is important. We really want to adapt to their practices. We want to make agronomic sense. We understand that other technologies to be implemented at farm level is complex. Again, biochar, because the benefit is not clear. They understand there's a sequestration element, which is good, but farmers, they have the organization trying to do a job. So in our case, we would love that input from them in how easy is the photocatalytic material to be applied. Also, for the scientific community, we still on the end-to-end measuring and understanding more about that. We're really happy to engage with the public, with the stakeholders, so they can have their own input on how to scale. How can we scale the measuring end-to-end? It's a very novel field. We know that there's not a lot of people doing a lot out there. Try to find them. So very happy for the community. Also, other stakeholders like local government. We really want to hear that. What are the objectives? How something like this could help at government level to really support the carbonization of the agricultural sector. So yeah, I think inputs on implementation, also in the end-to-end at a scale, and also how we can fit in the objective of government and local government in general.
Yeah, like based on your numbers at the emissions from agriculture, this could be really impactful solution.
Hopefully, yeah, we believe so, and the engagement with partners is very strong, and we believe that thanks to the collaboration with the scientific community, with the high regarded standards like yourself, we should be able to help everyone to make that impact.
Thank you. I think that's good to conclude with those words. I'm just gonna show you, because I couldn't do it before, where you can participate in the public consultation before we close. So if you can see my screen, we are on the Carbon Registry homepage. If you go to ICR program, go to public consultation on the left side here. Methodologies, choose 2025, and then you will find the ICR M-ICR number 11. And at the bottom of the page, you can go to this public consultation form that will guide you on how to provide feedback. And the public consultation is open until the 1st of May, the Labor Day. So let's conclude with that. And just thank you very much for your presentation. It's been a true pleasure being with you here today. And thank you all for attending the webinar. Thank you. Bye-bye.
Yeah, thank you everyone. Ciao, ciao. Bye-bye. Thanks.
Ciao.